In this lecture, we're going to look at using some of the thermochemistry we're learning to address some sort of practical kinds of problems and show you that the thermochemistry has actual real-life applications. I have 4 problems, and in the video recordings of these lectures, they're separated into 4 separate videos to keep them from getting too large or too long. In this one, we'll look at the first problem, dealing with the energy consumed in the form. So the problem is actually 2 parts. First of all, we assume a person consumes 2,000 food calories in one day, and food calories is something that maybe you should be familiar with, and 2,000 might be a typical number for For an athlete, for example, it's probably a lot more. But let's say we'll calculate the mass of the carbohydrate that's needed to supply that 2,000 food calories, and we can do that using thermochemistry. There's a follow-up to that, and the follow-up is what is the power consumption of the human body? Power is energy use per time, or the rate of energy use. And to calculate it, we take the total energy use, divide by, in a particular period, and divide by the time. And that gives us a quantity called power. So I want to emphasize power is something very different from energy. The standard unit of power is the watt, which is 1 joule per second. So it's 1 joule per second, and you might be familiar with this, this unit, say a 60-watt light bulb that uses energy at the rate of 60 joules every second. Okay, so now let's look at the first question, and the first thing we want to do is convert the food energy into a unit that's more widely used. We'll convert that energy into kilojoules. First of all, 1 calorie is 4.184 joules. That's a kind of a standard conversion, and I hope it isn't too much of a stretch for you to say immediately from that 1 kilocalorie is 4.184 kilojoules. I simply multiply by 1,000. And now the 2,000 food calories, what is that in kilojoules? I do a standard unit conversion, where again my equivalence relation here goes into a conversion factor here in such a way that the units cancel. And I get this number, 8,368 kilojoules. Now, now I want to relate that to the amount of carbohydrate. I'm going to use glucose as a representative carbohydrate, and the fact is that it doesn't really matter that much what carbohydrate I use. The answer for mass is going to come out to be pretty close no matter which carbohydrate I use. It's going to be very different for molar quantities, but for mass, in the end, when I calculate the mass of glucose, that would be the mass of, pretty close to the mass of any carbohydrate. So the first thing I do is I write a chemical reaction. Now, in metabolizing food, the chemical reaction is the overall chemical reaction is essentially the same as a combustion reaction. That is, the glucose reacts with oxygen, and in the end, it makes carbon dioxide and water. And the whole process is very complicated, but overall, this is what happens. And so I write this and I balance it, and you can look at the coefficients and confirm that it is balanced. Now, when I write this in doing thermochemistry, I think of this as standing for a mole, 1 mole of glucose, 6 moles of oxygen, 6 moles of carbon dioxide, and 6 moles of water. Now I look these up. I consult a table of heats of reaction or heats of formation or enthalpies of formation. And I can find these, you can find a table in the back of your book, and you can find them on the internet. You can find them all over the place, but you simply look up the so-called heats of formation. For glucose, it's this value, minus 1,273.02 kilojoules per mole. That is the energy change when I make glucose from its elements. I make 1 mole of glucose from its elements. And I look up the similar quantities for carbon dioxide, minus 393.5, and for water, minus 285.83. Notice I left out oxygen, and why did I leave off oxygen? An element in its standard state has 0 enthalpy of formation. The elements are sort of the scale against which we measure all the other enthalpies. That's what the enthalpy of formation scale is all about. So I can, in looking at this, I can just assume this one is 0. Now, to calculate the energy change or enthalpy change for this reaction, I simply take the products minus the reactants, and that is shown on the slide. Calculate the enthalpy of reaction, delta H. So I have, so notice how the units go here. The coefficients in the reaction stand for numbers of moles. So this is the CO2. The coefficient stands for 6 moles, and notice moles cancel. So 6 moles times the enthalpy of formation for 1 mole. Then there were 6 moles of water. This is the enthalpy of formation of water. 6 moles, 6 moles. And these are the products. And the reactant, I have the reactants are the glucose and the oxygen. Oxygen doesn't contribute. Its enthalpy of formation is 0. So I subtract 1 mole times the enthalpy of formation of glucose. And again, moles cancel. So when I do this, I notice when I carry out this calculation, I have to be very careful about signs. Notice that I have a minus sign here and a minus sign here, and so that contributes to my final answer. That's going to be positive. Enthalpies of formation are almost always negative, so it's very easy to mess up the signs when you do this. Confirm it for yourself, but when I carry out this calculation, I get minus 2,803 kilojoules. The implication of that, then, since I balance this equation for 1 mole of glucose, the implication of that is 1 mole of glucose can supply 2,803 kilojoules. Students always ask what happens to the sign of this. The energy available is the negative of delta H. This is an exothermic reaction, so the reactants lose energy as they react, and that energy is now available as heat. And so I'm actually looking at a positive number there. So 1 mole of glucose is equivalent to 2,803 kilojoules. The other thing I'm going to need, besides the equivalence between kilojoules and moles of glucose, in the end, I want the mass. And so the usual thing, I look up the molecular mass of glucose, add up the atoms, and I get 180.16 grams per mole. So I have 2 equivalence relations here and here that I can use in a calculation. And I convert the energy I got on the last page, this 8,368 kilojoules, using these two equivalence relations, and again, making the ratios such that the units cancel. So the first one converts the kilojoules into moles of glucose. The second one converts moles of glucose into grams of glucose, and I get 538 grams of glucose. That is somewhat more than 1 pound. And recall, this could be any carbohydrate. So 1 pound of dry carbohydrate is enough to supply all of the food calories that one needs in a day. That should seem like a reasonable number. To summarize, now I could do this, sometimes we like to do calculations like this all in one step. The first step was converting the 2,000 kilocalories into kilojoules. The second step, converting kilojoules into moles of glucose. And the last step, moles of glucose into grams of glucose to get my answer, 538 grams of glucose. Now look up the follow-up question. Given that this 2,000 kilocalories per day, or the 8,000 some kilojoules per day, what's the power consumption of the human body? All the energy that we use comes from the food we eat. And so at what rate are we using energy during the day? At what rate are we using energy? And this would be an average rate. There'd be sometimes when we're using more, sometimes when we're using less. But overall, what is the power consumption of the human body? Average. So I use the previous result. The energy in one day, 8,368 kilojoules. A kilojoule is 10 to the third joules. So if I convert into the standard unit, I get 8.368 times 10 to the sixth joules. Now, again, to do standard units, I'm going to want the time in seconds. So this should be a pretty straightforward conversion. The time is 1 day. 1 day is 24 hours. 24 hours is 60 minutes. 60 minutes is 60 seconds. And I carry out this calculation to get 8.6 times 10 to the fourth seconds. Power consumption is joules per second, so I simply divide my energy in 1 day by the time in seconds. I get 96.9 joules per second, which is, and a joule per second is a watt, 96.9 watts. This is the power. So the rate at which a person uses energy is roughly equivalent, about the same, as the rate at which a 100 watt light bulb burns energy.